Hi everybody, today we are going to talk about mathematical induction. So the principle of mathematical induction is essentially the process of doing a proof. So you're trying to prove that some statement or some formula is true in reference to some positive integer n. So here's the more technical definition right here, but I broke it down into 3 steps where we're going to pretty much follow some version of these 3 steps. Here they are. Step 1 is the first thing you are always going to do is show that your formula that you're trying to prove is true when n equals 1. That's always going to be your first step in mathematical induction. Step 2 now is where it gets a little bit different. This might be very, something completely new to you. We're going to make an assumption. We're going to assume that the formula is valid for some integer, which we're going to call k. We're just going to state it as a fact and make the assumption that it's true. Then step 3, after we've made that assumption, is to show that it's also true for the next integer, which we'll call k plus 1. So then we'll go through the process of showing that k plus 1 also works, and we will be using that assumption that we made in step 2. Okay, so let's give this try. Oftentimes the way that it's written can look a little bit overwhelming, but really all that's happening here is that I have an arithmetic sequence. So here the rule for our sequence is just 2n minus 1. So you could either get that by actually looking at the pattern and creating it, but they actually tell us the next term is just 2n minus 1. And then they want us to prove that the sum of the first n terms is n squared. So we're going to follow those 3 steps to prove this. So remember, step 1 is to always check to make sure that n equals 1 is true for the thing we're trying to prove. So according to our formula, the sum of the first 1 term should be 1 squared, which is 1. Now if you look at your sequence, a sub 1 is 1, so this is true. That formula works for n equals 1. So now we're going to make that assumption. We're going to also assume that the formula works, that this formula works for k, some integer. So we're going to say s sub k equals k squared. We're going to treat this as a fact. And using that, now we have to show that the integer k plus 1 also works for this rule. So if I substitute k plus 1, I'll get k plus 1 quantity squared. So we're going to try to create something that looks like this. And if we can, then we know that our formula is true. But before we do that, there's a really important concept that you have to understand. And to do that, I'm going to start by giving a actual number example, and then I'm going to start using variables. So let's assume hypothetically that I tell you the sum of the first 10 terms in some sequence is 25. Well, if the sum of the first 10 terms is 25, that means that the sum of the first 11 terms would just be the sum of the first 10 plus whatever that next term is, a sub 11. So we're going to kind of use this idea, and we're going to say that the sum of the first k plus 1 terms is just the sum of the first k terms plus that next term k plus 1. So remember, that's just like saying that if the sum of the first 10 is 25, the sum of the first 11 is that sum plus 1 more term. So that's what we're doing here, that sum plus 1 more term. So the next thing we can do is we can actually substitute right here. We've already defined s sub k as k squared. We are making that assumption and we're stating it as a fact. So I'm going to substitute k squared for s sub k because we are assuming that they are equal. Now I need to figure out what this is. So this will be the k plus 1 term in our sequence. So remember, our rule for the sequence, which is up top, is 2n minus 1. So if I'm trying to find k plus 1, I say 2 times k plus 1 minus 1. So that term is just 2k plus 1. So I distributed and combine like terms. So I'm going to substitute this with what the term is, 2k plus 1. And And then if you look at what we have left, you notice that it can be factored, and it actually becomes k plus 1 squared, which is exactly what we were trying to create. So when you give something like that, you have just proved that that is true. So we can say, like, therefore, the sum of the first n terms is n squared for that sequence. There you go. So that is the process of mathematical induction. All right, go ahead and pause the video and see if you can give this problem a try. So remember, here they're just saying this is our sequence and this is what they're asking you to prove. All right, go ahead and check your work. So make sure you have step 1, which is checking to see that your formula works for n equals 1, which it does. And then you're making the assumption that S sub k is true, that this formula works for the term k. And then we want to show that S sub k plus 1 is also true. So remember, I go in and I substitute k plus 1 here and here. So k plus 1 becomes this, and then k plus 1 plus 4 becomes k plus 5. And then here's that jump that I really need you guys to make, that the sum of the first k plus 1 terms is just the sum of the first k terms plus that next term. So here's how you find the next term, by plugging it into your formula. This is our given, or our assumption, so we can substitute it. And then once you combine like terms and try to factor, you end up with exactly what we were trying to show. Okay, this next type of problem, we're going to follow that same exact process. All right, so here we can see that the sequence is defined by the rule n squared, and they want us to prove that the sum of the first n terms is n times n plus 1 times 2n plus 1 all over 6. So let's follow those same 3 steps. Step 1 is to check n equals 1. So the sum of the first 1 terms is 1 times 2 times 3 over 6, which is 6 over 6, which is 1. You can see that the first term in our sequence is 1, so this is true. So step 2, we can make our assumption. We're going to assume that this rule works for the integer, or for the integer k, that it is a true statement. So saying if you substitute k, it will work. So k times k plus 1 times 2k plus 1 over 6. We are going to use this as a fact. We're going to substitute it later. Now step 3, we have to show that that rule also works for k plus 1. So I'm going to substitute k plus 1 here, here, and here. So we get k times k plus 1 times 2k plus 3, which came from 2k plus 2 plus 1. And all of this should be over 6. So this is what we are trying to prove, or this is what we would like our equation to look like by the time we're done. And if we can make it look like that, we know that that formula is in fact true. So that first jump is, remember, recognizing that we can split this up into S sub k plus A sub k plus 1, the sum of the first k terms plus that next term. So the sum of the first k terms we've already defined in step 2. So I'm going to substitute it right here. I'm sorry, this should have said k, not n, and over 6. And then we still have to find A sub k plus 1. So I would just go in and plug in k plus 1 into our sequence. So it becomes k plus 1 squared. From here, it's just a matter of simplifying, but there's definitely an easy way and a hard way that you can go about this. So the first thing you're going to want to do is combine the two terms into one fraction. So we have k times k plus 1 times 2k plus 1. And I'm going to need to multiply this term by 6 over 6. And now I have a single fraction. So from here, you can look for a GCF. So I notice that both of these terms share k plus 1 as a factor. So we can actually factor that out. So k plus 1. What we have left from our first term is k times 2k plus 1. And what we have left from our second term is 6 times k plus 1, and all of that is over 6. Now from here, I'm going to distribute and combine like terms within my brackets. So when I do that, I have k plus 1 times 2k squared plus 7k. So I have k here plus 6k here, and then I have plus 6. And now this, I can take one more step and I can factor it. So I end up with k plus 1 times k plus 2 times 2k plus 3 over 6. And if you look back, this is exactly the scenario that we were trying to create. So since we have shown that it works for k plus 1, we know that that statement is true. All right, go ahead and pause the video and give this problem a try. All right, and check your steps. So make sure you have checked for n equals 1. Make sure you have your correct assumption, which you're going to be substituting, and make sure that you are showing that this statement is true. So after you've done your substitutions here and here, and you combine it into a giant fraction, factor out a GCF of k times k plus 1, you should end up exactly with what you wanted to show, proving that it is true. All right, so here we're trying to prove that an inequality is true for all integers n is greater than or equal to 1. So it's a little bit different, but we're still going to use that same general process, just a few different little tricks to help along the way. So our first step is still going to be to check n equals 1. That's always our first step. So if I plug that in here and here, I see that it is a true statement. So step 2, we're going to make our assumption that this inequality is true for the integer k. So we're saying as a fact that k is going to be less than 2 to the power of k. So from there, we now need to show that k plus 1 is less than 2 to the power of k plus 1. So now that we have our general setup, now we just have to go through the process of actually showing that this is a true statement. So for this problem, I'm going to do some of the work on this side. So I'm going to work with this part, 2 to the power of k plus 1. Up in our assumption, I see that we can assume that k is less than 2 to the power of k. So we want to try to find some way to rewrite 2 to the power of k plus 1 using 2 to the power of k. The more we can use our assumption statement, the better. So I look at this and I want to rewrite it in terms of 2 to the power of k. Well, I know that 2 to the power of k is very, very close to 2 to the power of k plus 1. I just need to multiply it by 2 one more time. This is kind of equivalent to saying, okay, 2 to the power of 10, we can rewrite that as 2 to the power of 9. But we are 1 short, so we could rewrite it just like this. So just remember, we always want to try to rewrite our statement in terms of our assumption statement. So just by doing this alone, we're already a little bit closer. And from there, since we have 2 times 2 to the power of k, we can rewrite that as 2 to the power of k plus 2 to the power of k. So I'm going to start by rewriting this inequality, but backwards. So I'm just going to put this side on the left. There we go. Okay, so we know, we've shown over here that I can write 2 to the power of k plus 1 as 2 to the power of k plus 2 to the power of k. So I'm going to rewrite this inequality with that substitution. So remember, we're trying to show that this is greater than k plus 1. So the first thing that we can change about this statement is, well, using our assumption statement, I know that 2 to the power of k is always going to be bigger than k. So if I take this and I replace it with k, but I keep the other part the same, all else being equal, these two things are still equal. I know this expression is smaller than this expression because I know that k is smaller than 2 to the power of k. This I can do by assumption. Okay, so I know that this expression is less than this expression because these parts are equal and this part is for sure smaller than 2 to the power of k. That's assumed in step 2. Now here I can also look at this, and here I'm just going to kind of use a little bit of common sense. That k is going to stay the same, but another thing that I'm going to look at is right up here. I'm trying to show that it's that this is greater than k plus 1. Well, I know for a fact that 2 to the power of k is always going to be bigger than 1, because if you look at your original question, it says n is always greater than or equal to 1. So the smallest thing that this term could possibly be is 2. So I know that this statement is always going to be greater than 1. And this isn't by assumption, this is just number sense. It's just understanding that given our restriction, this is always going to be bigger than 1. So I guess we can say that n is always greater than or equal to 1, and that's how we can change this part. But once again, I know that this expression is smaller than this expression because everything else is the same except for this part, which we know is true. And I know that this expression is smaller than this expression, and I know that this is equal to that expression. So we have essentially just shown that 2 to the power of k plus 1 is greater than k plus 1, because 2 to the power of k plus 1 is equal to this, which is greater than this, which is greater than k plus 1. So we kind of worked our way there. So therefore, we have shown, we can say therefore, n is always going to be less than 2 to the power of n. For all integers, n is greater than or equal to 1. And there you have it. All right, so go ahead and pause the video and give this problem a try. All right, so go ahead and check your work for this problem. So here first we always check to see that our statement is true for n equals 1, which it is. And then we're going to assume that our statement is true for some integer k. So here's our assumption, which we're going to substitute later. And then the way that we can prove by induction is by showing that k plus 1 is also true. So for here, it's really important that you remember that k plus 1 factorial is just k factorial times k plus 1, right? It's everything up until 1 times 2 times 3 times 4, so on until k, and then multiplying one more, the term right above it. So I'm going to replace this part of my statement with this, and then I'm going to start making statements about what this is greater than. So first of all, I know that k factorial is greater than k, or equal to k. It is certainly greater than or equal to k. That's an assumption that I can legally make. So I've replaced this with this. And then I've rewritten this again. And then over here, according to our assumption, or a legal statement that we can make, is that if you have k times k plus 1, that's certainly going to be bigger than just k plus 1 by itself. And once again, we know this because it says in the problem that n is an integer greater than or equal to 1. So we can use that statement to help us kind of change this into this. But our first statement should certainly be rewriting k plus 1 factorial as k factorial times k plus 1. And then from here, I wrote those same steps again, except instead of this first term, I just used the term that we were using, just to be a little bit more formal, but it's not even entirely necessary to do. But we have shown that k plus 1 factorial is greater than or equal to k plus 1, which therefore proves that that statement is correct. All right, the last type of problem that we're going to be proving is we're going to prove that something is a factor of another expression that has an integer n. So here we're going to prove that 3 is a factor of this expression, 4 to the power of 1, or 4 to the power of n minus 1. So same general process. We all know that step 1 should be checking n equals 1. So if I substitute that in, I have 4 to the power of 1 minus 1, which is 3. Well, 3 is certainly a factor of 3, so this first statement is true. So now step 2 is we're going to make our assumption that this is true for the integer k. We're just going to assume that 3 is a factor of 4 to the power of k minus 1. And you do need to write out 3 is a factor of 4 to the power of k minus 1. We're assuming that this statement is true for the integer k. Now, after that assumption, now we have to show that 3 is a factor of 4 to the k plus 1 minus 1. We have to show that this also works for the next integer, which we'll represent as k plus 1. Okay, so the process of proving that 4 to the power of k plus 1 minus 1 is a factor of, or that 3 is a factor of 4 to the power of k plus 1 minus 1 is a little bit different. There's this little trick that makes these problems infinitely easier. So what we're going to do is we're going to try to create a scenario where we see this expression, 4 to the power of k minus 1, because it is something that we know is divisible by 3. So if we can create this, then we can, we're one step closer to showing that 4 to the power of k plus 1 minus 1 is also divisible by 3. So I'm going to spread this out, give yourself some space, and I'll show you why in just one second. I see that there's already a minus 1 here, and I know that I want 4 to the power of k minus 1, so I'm just going to add it in right here. But of course, this is an expression. I can't just add in something and change it completely. So in order to combat that, I'm going to subtract it right here. So you can see that since I've added and subtracted the same thing, I haven't really changed our expression at all. But I have created a scenario that I really like. So we really like to see that 4 to the power of k minus 1. So now we have to deal with what's left over here. And this is kind of a scenario where we can group it and factor. So here I see that there's a common factor of 4 to the power of k. So if I have 4 to the power of k plus 1 and I factor out 4 to the power of k, I'm left with 4 to the power of 1, which is just 4. Here I factor out the entire thing, so I'm left with 1. And then here I still have that expression, which we really like. Now look at what we have left. We have 4 to the power of k times 3 plus 4 to the power of k minus 1. So this first part, we know that 4 to the power of k times 3 has a factor of 3. And we know that it has a factor of 3 because it says times 3 in that expression. So that is something where you don't need to say anything else. I can see times 3. I know that it has a factor of 3. It's divisible by 3. Now that second part, that 4 to the power of k minus 1, also has a factor that is 3. And I know this by assumption. So this is that exact assumption that we made up here in step 2. We assume that 3 is a factor of 4 to the k minus 1. So since 3 is a factor of this term and 3 is a factor of this term, we have now shown, we can say, therefore, 3 is a factor of 4 to the power of k plus 1 minus 1, which is exactly what we needed to show. All right, here is the last problem. Go ahead and pause the video and give it a try. Okay, let's have a look. So same process, first check n equals 1, and then we're going to assume that 2 is a factor when we use the integer k, and then we have to show that 2 is a factor when we use the integer k plus 1. So we're going to do that same process of adding and subtracting that 3 to the power of k. So when we factor it out, we have 3 minus 1, which is 2, and we have 3 to the power of k plus 1, which by assumption is has a factor that is 2. So you can kind of break this up into 2 separate parts, showing that both of them have a factor that's 2, proving that your entire thing is true. All right, that's all for today. Thank you so much for watching.